In this screencast, we are going to talk about the thermodynamics of bond breaking and bond making and how they apply to reactions. Now, bond breaking can be quantified using bond dissociation energy. So, bond dissociation energy is just the energy needed to homolytically cleave a covalent bond. Okay, so homolysis, anytime you're breaking a bond, that's going to require energy. Okay, and so we measure that with bond dissociation energy. Now, I want to remind you there's this little H here, and that also is enthalpy, which you probably talked about in general chemistry, either one or two, right? Now, because bond breaking always requires energy, bond dissociation energies are always positive numbers, and homolysis is always endothermic. So, because bond breaking requires energy, bond dissociation energies are always positive numbers, right? And that means that homolysis is always endothermic. Now, there's the other side where we are forming bonds. And so bond formation always releases energy. And therefore is always exothermic. Now, this is demonstrated for you here in these two examples. We're looking at the bond in H2, right, hydrogen, and it requires 435 kilojoules per mole to break or to cleave, right? And that's an endothermic reaction because there's that positive there, okay? So that's one of the ways that we can recognize that it's endothermic. Then, for those bonds to form, that's an exothermic reaction where we are giving off energy when they form, and so that's exothermic. Notice that the values of when you break the same bond and when you form the same bond, those values are the same. We just change the signs, okay? Now, there's a table in your book that has the common bond enthalpies. Do not memorize these numbers. If you have to use this on a test or an activity, you can look it up in the book, or I will give it to you. Like if it's on a test, I will give you the numbers. But here are some bond dissociation energies for just common bonds. Now, I want to draw your attention to something. If you're solving a problem and it's a carbon-chlorine bond, it does matter what type of carbon that, like for example, that chlorine is bonded to. So you do need to look over here and see, is it bonded to a CH3? Is it bonded to a CH2? Is it bonded to a CH? Or is it just bonded to a carbon? Because you can see those values are really different. That's the thing that most commonly trips students up when they're solving problems like this, is just they look at the wrong value. So do pay attention and double check not only what bond you're looking at, but what groups are next door or next to it. Now, when we compare some bond dissociation energies, that is comparative to looking at bond strength, right? So what we see here is that the higher the bond dissociation energy, the stronger the bond, right? So what we see here is increasing bond strength from a carbon iodine to a carbon bromine to a carbon chloride to a carbon fluorine. And so that to us indicates that, look, this bond here is going to be the strongest bond. Okay. Now, there's a trend here, and the trend that we have is that bond dissociation energies decrease down a column of the periodic table as atom size increases. So these fluorine, chlorine, bromine, and iodine are on the halogen column, and as you go down that column, iodine is going to be the largest. That means, right, that it's going to end up being the weaker bond. And the reason that we see this is that iodine is really large, and so the electrons there are just a lot more spread out, whereas fluorine is really electronegative. It holds on to its electrons really tightly, and that forms a kind of closer bond here, okay? So because this bond is closer, because fluorine is smaller, and then over here iodine's really, really big, so that means this bond is longer, right? What we find is that in general, shorter bonds are stronger bonds, right? Because over here, this is a longer bond because iodine is huge, right? And over here, right, this is a shorter bond because fluorine is small. Right. And so those are some of the ways that we can identify where we've got shorter bonds and stronger bonds, is to look at the atom size. Bond dissociation energies are also used to calculate energy change. So when we talk about energy change in reactions, and we look at this, right, we are interested in the overall enthalpy change. And so to do this, you look at the sum of the bonds that are broken and add them to the sum of the bonds that are formed. And this is just a reminder that, hey, look, you're going to flip this sign. It's going to be negative, okay? So bond dissociation energies are going to be used to calculate the enthalpy change in a reaction where several bonds are broken and several bonds are formed. So when that delta H naught of the overall reaction is positive, right, that tells us that more energy is needed to break the bonds than is released forming the bonds. Okay, that means that the bonds broken in the starting material are stronger than the bonds formed in the product. Okay. Now, let's look at what happens when we look at the inverse here, which is, or the opposite. When those delta H naught is negative, right, more energy is released forming bonds than is needed to break the bonds. Okay, so that means the bonds formed in the product are stronger than the bonds broken in the starting material. Okay, so let's do an example. If you were asked to calculate this. So this says use the value in table 6.2 to determine the enthalpy for the following reaction. So when we do this, we need to, when I start problems like this, what I do is the first thing I do is I write down the equation I'm going to use so that I know how to gather the information. So I say, okay, look, I am going to determine the enthalpy here for this reaction. So I know that the change in enthalpy for the overall reaction equals the sum, and I'm going to show sum like this, right? That's just the mathematical symbol for sum, of the bonds that are broken plus, right? And I'm going to remind myself that these are negative, right? The sum, ooh, my sum got really wild there. The sum, right, of the negative bonds formed. Now, some books are going to present this material where they don't have you flip the sign, where they just say, look, you take the bonds broken and you subtract the bonds formed. I don't care which one you use. Both are going to give you the same answer. My suggestion is to use what works best for you. So depending on how you learned it in general chemistry, my suggestion would be to continue to do that just because it'll be easier for you, right? And we're all about kind of what's easiest here. So I'm going to continue on like the book does, okay? So when we look at this, we need to look and think about what bonds are broken between this reaction and then what bonds are formed here, okay? So when I look at this, I say, okay, hey, look, one of the things that changes when I analyze this is that this Cl is no longer bonded to this carbon, and in its place is an OH. Looks like a substitution reaction. So I'm going to highlight in yellow that bond is broken, and then I'm going to come over here and let's highlight in blue that bond is formed, okay? And then I'm going to look at, right, what's going on over here with my OH, H2O, and my HCl. And one of the things that I see, right, is that this bond here is going to be broken so that it can form, OH can form this bond. So this bond is also broken, okay? Then, sorry, I'm going to make those see if I can make those a little darker. Okay, then I'm going to see what bond forms over here, and we can see that this HCl bond is going to be a new one that forms. So we're looking kind of for the bonds that change between the reactants and the products. So now let's look at the bonds that are broken. Okay, so we've got that CH3, and there's 3 of them there. So 1, 2, 3, and there's a central carbon, Cl, okay? And the delta H for that is positive 331 kilojoules per mole. Then the other thing that we have broken is the OH-H bond, and that's positive 498 kilojoules per mole, okay? And we are going to add those up. So we add those up, and that gives us 829 kilojoules per mole. And that is everything that is the energy that's needed to break those bonds, okay? Then we're going to come over here to the bonds formed. When we look at the bonds formed, we are forming a bond CH3C, and there are 3 CH3s there, OH, okay? And so that delta H there is going to be negative 401 kilojoules per mole. Then we're also going to form HCl, and that's going to be negative 431 kilojoules per mole. So we are going to add these two together, and this gives us negative 832 kilojoules per mole. So that's kind of our first two steps, is we analyze the bonds that are broken, and we calculate up the enthalpy, and then we analyze the bonds that are formed, and we calculate up that enthalpy too. Then for our third step, what we're going to do is we're going to come down here, and we're going to figure out the overall delta H. So we take those bonds that are broken, the 829 kilojoules per mole, and then we are going to add the negative 832 kilojoules per mole. And so this gives us the answer, negative 3 kilojoules per mole. Now, what does this tell us about the reaction? Well, our delta H naught value for the overall reaction is negative. And so because it's negative, that means this is an exothermic reaction. And energy then is released. Now, that also means the bonds that are broken in the starting material are weaker than the bonds that are formed in the product. Okay. Now, so this is a really helpful tool for scientists. This tells us, is it going to be exothermic? Is it going to be endothermic? Would we expect heat to be released? But there are some limitations here. So when we talk about limitations on doing this, let me move that kind of fellow up there, right? Bond dissociation energies really present overall energy changes, and they don't tell us anything about reaction mechanisms or how fast that reaction proceeds. So our limitations here for using this bond dissociation energy is there's no information about the reaction mechanism that's step by step to tell us how those electrons are moving or how fast this goes. Right? If this reaction, so this reaction is exothermic, and that means it's going to release energy. But if it takes us, 30 days for this reaction to go to completion, that's a problem. If we need a product by next week, right? So other kinetic information and thermodynamic information is very helpful. The other limitation here is these bond dissociation energies are determined in the gas phase. Right? And most organic reactions occur in liquid solvent. Right? And so in liquid solvent, what you're going to have there is a solvation energy. And that solvation energy is really going to contribute to the overall enthalpy. Now, even though bond dissociation energy is imperfect, calculating the delta H does give us a useful approximation of the energy changes that occur in the reaction. So it is helpful. Okay. Now, we mentioned, though, that knowing a little bit more about the reactions, whether they're going to be practical, it would be helpful to have some other thermodynamic quantities. And so for a reaction to be practical, the equilibrium must favor the products, and the reaction rate must be fast enough to form them in a reasonable time. So these two conditions depend on more thermodynamics and kinetics. And remember, kinetics is just the rate or the speed of the reaction. So thermodynamics is a quick reminder, just talks about how the energy of the products and reactants compare. And the relative amounts of reactants and products at equilibrium. And a lot of times, right, we think about equilibrium as when that reaction is complete or finished, right? But remember, at equilibrium, when we're no longer producing any additional products, right? We're not going to always have, or many times we're not going to have 100% products. We're going to have some percentage of products and some percentage of reactants. Now, kinetics, right, is going to describe reaction rates. And that's just how quickly reactants are converted to products. So one of the tools that we use for this is the equilibrium constant. So when we think about the equilibrium constant, that is just a lot of times shown as KEQ. And that's just a mathematical expression that relates the amount of starting material to the product, the amount of product at equilibrium. So it will tell us, it's really very helpful, it will tell us, do we have more reactants or products at equilibrium? So just to do a quick refresher on KEQ, right? You probably remember a generic reaction that looks like this, where the lowercase letters are the coefficients and the uppercase letters are the chemical species. And when we talk about KEQ, we take the concentration of the products over the concentration of the starting material or the reactants, right? And so that gives us the concentration of C raised to the coefficient times the concentration of D raised to that coefficient over the concentration of A raised to A and the concentration of B raised to B. I want to remind you that these brackets just mean concentration of, so don't use parentheses, and that these are the coefficients that it is raised to. Now, what does the value of KEQ tell us? Well, the size of KEQ tells us whether the starting materials, right, or the products are mostly there once equilibrium is reached. So, for example, if KEQ is greater than 1, what that means, if we look at any fraction, right, and any fraction's greater than 1, it means we're going to have more things in the numerator than the denominator. So that means that equilibrium favors the products. Now, a lot of times, you can hear this referred to a couple different ways. Sometimes you are going to hear this referred to as the equilibrium lies to the right as the equation is written. So we're going to say, maybe, there we go. We're going to say the equilibrium lies to the right. Okay. If KEQ is less than 1, that means that, right, we have a larger number in the reactants than the products, or in the denominator than in the numerator. So we have a bigger number of reactants than products. So that equilibrium favors the reactants, and the equilibrium then lies to the left. Okay. Now, if KEQ equals 1, then you have an equal amount of reactants and products. Now, for a reaction to be useful to us, equilibrium needs to favor the products and the KEQ needs to be greater than 1. So we need this for a useful reaction. Now, the position of equilibrium is determined by the relative energies of the reactants and products. So we have to take into account that enthalpy that we talked about previously. We also have to take into account entropy as well. Now, there's a value that does this, and this value is Gibbs free energy. And we're going to talk about Gibbs free energy here. When we talk about Gibbs free energy, and that was named after a scientist called Gibbs, so a lot of times we're starting to kind of drop some of those names and just call it free energy, but the problem is it's still delta G for us. So Gibbs free energy, to me at least right now, makes a little bit more sense, right? This is just the overall energy difference between the reactants and the products. And so here is the big take-home message. If your Gibbs free energy is greater than 0, right, your KEQ is less than 1, equilibrium favors the starting materials. Okay? If your delta G is less than 0, that means your delta G is going to be negative here. Over here, your delta G is positive. We're going to look at those negatives and positives. Then your KEQ is greater than 1, right? And that means that you have more stable products, and equilibrium favors the products. Again, delta G is negative. This is a useful reaction for us, right? We want to make more products at equilibrium. Now, delta G is related to the equilibrium constant by this reaction here, okay? Where if KEQ is greater than 1, that makes the log of KEQ positive, and then that makes delta G negative, okay? And energy is released and equilibrium favors the products, just like what we talked about on the following slide. If KEQ is less than 1, then that means the log of KEQ is negative, and that's what makes delta G positive, and that's where we see energies absorbed and equilibrium favors the reactants. So this is how delta G and KEQ are related and why their signs are inverse. So when, like, for example, KEQ is positive, delta G is negative. And then when KEQ is negative, delta G is positive. I want to point out this log for just a second, okay? When we look at this log value here, a small change in your delta G energy corresponds to a large difference in the amount of starting material and products at equilibrium. And this, as a student, this blew my mind, right? So if I have a delta G of 18, that means essentially everything that I have is A. When I look at a generic reaction that goes from A to B here, right? If it is positive 18, I've got mostly A. If it is positive 6, I have 10 times as much A as B. And then if it's 0, KQ equals 1, it's equal amounts. Then if it's negative 6, I have 10 times as much B. And then we double that, negative 12. And look, this goes up tenfold, right? It's 100 times more. And then negative 18 means you essentially have all B. So very little variation in the delta G will really affect your amount of products and reactants here. So, right, when we talk about this, equilibrium favors products when they're more stable than the starting materials. That's kind of the take-home message. So we're going to talk a lot about reactions and stability. And we're going to say, hey, look, right? Equilibrium favors products when they're more stable. Well, equilibrium is also going to favor the reactants when they're more stable. So that means a reaction will proceed, right, when the reactants are more unstable than the products. Okay? Now, compounds that are lower in energy have increased stability. Okay, so I want us to think about this. If we have A going to B, right? If we say the product is more stable than A, right? Then that equilibrium favors the product. Another way to say this is that the reactants are less stable than B. Okay, so you have to look for both of these context clues. When we are talking about equilibrium favoring the products, if something is less stable than the product, it's going to react to form the product, right? Another way to say that is if the product is more stable, right, then it's more likely to form. So you're going to hear those both ways when we talk about reactions in organic chemistry. And so it's just helpful to think about that, okay? Now, equilibrium favors the reactants, right, when the products are less stable. Right? And another way to say this is that over here, the reactants are more stable than the products. So a lot of organic chemistry is a comparison game. And where things are less stable and more stable will help us figure out, look, is this going to favor the products or not? Now, another thing that can help us with this is entropy, right? And entropy is just a measure of randomness of the system, right? And the more freedom of motion, right, or the more disordered, the higher the entropy, right? So, for example, gas molecules move more freely than liquid molecules. They're higher in entropy. Cyclic molecules have more restricted bond rotation. So they are less, let me say this, they are lower in entropy compared to linear molecules. Okay, so entropy favors the products here. So when entropy increases, from reactants to products, products are favored. Okay, and you can see an example of this here. We have a single reactant. Now we have two products. There's more motion here. There's more freedom of motion because you have two things instead of one. And so now the entropy increases and entropy favors the products here. When entropy decreases, from the reactants to the products, the reactants are favored. Okay, so for example, this is a linear molecule here. There's more freedom of rotation around the bonds. When it becomes cyclic, there's lower entropy here, so the entropy decreases, so the entropy favors the reactants. Now, the entropy is not the end-all be-all here, okay? And I also want to point out the signs you're going to see. If entropy increases, the delta S here is positive, and then if entropy decreases, the delta S is negative. So entropy is not the end-all be-all. But it is something we have to take into account when we're deciding if the reaction is going to be favorable, right? And so delta G, as I mentioned previously, takes into account the entropy, right, here, the temperature, because as temperature increases, the motion, the molecules move faster, so there's more motion, as well as the enthalpy here, that change in bond energy. So the total energy change that we see is really due to two factors: the change in bonding energy and the change in disorder, right? And so when we talk about that bonding energy, that's really calculated from our bond dissociation energy, so that's that enthalpy value there. Now, in most reactions that are not carried out in high temperature, right, the entropy term is really small. Compared to that enthalpy. So we can make an approximation. And our approximation is that means that delta G naught is approximately the same as the enthalpy, okay? Now, according to this approximation, that means the product is favored when delta H naught is negative, because then delta G is negative, because we can mostly ignore entropy. And then the starting material is favored when delta H is positive, because then that Gibbs free energy is positive. Now, I want to point out, right, that you will go on to other classes and you will go back and you will use that entropy value. But this approximation works pretty well for us all the way through the class. And so that's what we're going to operate under as we go through the rest of this class. In the next screencast, we are going to jump more into diagrams, right? So we are going to look at how we visually represent these energy diagrams, where we're comparing those reactants to the products, and then we're also going to talk about kinetics. As always, if you have questions, please feel free to stop by my office.